shared with all of you, and it is a quite extensive introduction to quantum computing, practical aspects of quantum computing, then the way the quantum computing can be implemented using various toolkits. So these are all things that are covered in the previous classes, previous sessions. So in particularly, my talk is going to focus on the security aspects of quantum computing and the quantum computing, how it is influencing the security. I hope my slides have moved and you are able to see the second slide, just to confirm.
Yes, sir. It is
Okay.
visible.
Yes, sir. So my session is going to talk about the cryptography in general, and then I'll be focusing on a couple of cryptography algorithms, which includes the asymmetric algorithms such as RSA and Diffie-Hellman. Then I'll briefly touch about the quantum computing principles, which perhaps already you have got exposed to in the last few days. Then I'll talk about, because of the quantum computing, what is the influence on security in terms of threats to the current cryptography standards. What are the challenges? Then I'll talk about few algorithms such as Shor algorithm, which is mainly aimed at identifying the factors of a given number, which is a quantum algorithm. Then I'll talk about quantum key distribution through BB84 protocol, which is there for key distribution problem. So both are quantum algorithms. Then I'll talk about the what is the roadmap ahead to make the quantum resistant security. So in the digital world, we are aiming at making secured communication. Right? All of us want secured communication. Security by means we are trying to achieve all these aspects. One is confidentiality, integrity, authentication, and above all that we have other aspects such as availability. So these are all various aspects of security we are aiming to achieve in the digital world. So all our communications we want it to be secure. In terms, when we say secure, we are aiming at achieving confidentiality, integrity, authentication, and all that. So these principles of security, which includes confidentiality, integrity, authentication, availability, non-repudiation, then digital signature, all these principles provide an assurance so that whatever the information that we share, whatever the communications that we make online or the communication network, they are all trustworthy and they are available only to the authorized users and not to the unauthorized users. That means we are aiming at security. So how do we implement security? For that purpose, obviously, we are basing all our security protocols and standards on cryptography. So if you see, the secured information is typically classified based on the expectations that it will remain secret for a particular duration of time. That means when I'm trying to secure some piece of information, say take an example, I want to secure my question paper that I have set. So obviously I'm expecting that particular question paper to be secure at least till the commencement of the examination. So that means till the examination time, if I secure my question paper, then it is sufficient enough for me, because after the commencement of examination, now the question paper is in the open domain. So for any piece of information, we are expecting that that particular piece of information is remaining secret till for the duration of a particular expected time. It is not that we expect that communication or the information to be secured forever. So all the algorithms that are using the regular mode of conventional computers are engineered in such a way that the cryptographic algorithms are strong enough to support at least a 25 years of service lifecycle requirement. Okay, so that means if my security algorithm or my cryptographic algorithm is able to provide security to my information a particular period of time, okay, then I can say that yes, I am having security to my piece of information or to security to my piece of communication what I am making. So all our traditional or conventional security algorithms which are using the conventional classical computers, all these algorithms are built such a way that the communications and the data is secure till a particular duration of period. But however, the current developments, especially the quantum computing, that is making that even the algorithms that are providing security will no more be secure even till the duration of period. So why it is happening, how it is happening, we will see. The reason is, especially in 1994, Peter Shor has come out with an algorithm which is mainly meant for algorithm to get executed on a quantum computer. So if that algorithm is implemented on a quantum computer, whatever the security strength that the current cryptography algorithms that have can be easily broken. So these points we will discuss in the in this particular talk. So my talk, as I mentioned, will explore the cryptography techniques, which includes public key cryptography such as RSA, and also I will be talking about quantum principles. Then subsequently, I will talk about Shor algorithm and its implementation. Then also BB84 algorithm for key distribution or key management. Especially this is BB84 is meant for key distribution. Shor algorithm is meant for finding the factors of a number. So these two algorithms are going to be covered this particular today's talk. So when you look at the cryptography, it has evolved a lot, starting from classical cryptography of the ancient times till the current modern cryptography. Okay, so there is a lot of literature available about the evolution of cryptography. So the modern cryptography is the current day standards, which includes symmetric as well as asymmetric crypto systems. The symmetric crypto systems, as all of us know, we are going to take the plain text, encrypt with a key, and the same key is going to be used for the decryption. So that means at the sender, when we are encrypting the plain text with a particular key, K, say K, same key would be used at the receiver to perform the decryption. So and hence, since the same key, that is the single key that is used, we are calling it as symmetric key crypto systems. Then when we have symmetric crypto system, when we implement it, obvious challenge is how both communicating parties, that is the sender and receiver, will have the common key. So how do I share the key commonly between both sender and receiver? So this is the main challenge. So when I have a symmetric crypto system, my challenge is sharing of key. So if I am implementing symmetric crypto system, I'm encrypting with the key and decrypting with the same key at the receiver. How do I have common key between both these communicating parties? So that is the fundamental challenge with a symmetric crypto system. In second approach, we have asymmetric crypto systems, wherein which we are having one key for encryption purpose, which we call it as encryption key, and another key for the decryption purpose, which is called KD. So at sender, I am using one key for encryption purpose, and at receiver, I am using different key for decryption purpose. So by doing this approach, I am able to solve this particular challenge. What is the challenge? The sharing of key is no more required because I am using two different keys. So at sender, I am using encryption key, and at receiver, I am using decryption key, and both keys are not equal. KE is not equal to KD. Both are different keys. And since it is two different keys are used, you call it as asymmetric crypto system. And there are other names to that called public key crypto systems. Public key crypto systems. This is also called as public key crypto system. In symmetric crypto system, the most popular algorithm is advanced encryption standard, which is current standard approach. Okay, so advanced encryption standard is the popular symmetric encryption algorithm, which is taking the plain text, divide into multiple blocks, and perform certain transformations. If you see here, there are about, you take the plain text, put it in the form of a state matrix, take the plain text, put it in the form of a state matrix, apply 4 types of transformations. These transformations called substitution of bytes, shifting of rows, mixing of columns, add round key. These are all 4 transformations that we do. These 4 transformation we repeatedly perform certain number of rounds. Okay, so finally we get a ciphertext. And I'm not going to cover this particular standard because it's a symmetric standard. So this is not our current point for discussion. But then I just wanted to show this to you that the current standard of symmetric encryption is advanced encryption standard, which is predominantly used. So which is the symmetric standard. In asymmetric, what we are doing is, it's also called as public key cryptography. We are using 2 separate keys, in contrast to the symmetric encryption schemes, which uses only 1 key. By performing encryption with the 2 keys, we are able to achieve number 1, obvious security objectives such as confidentiality, authentication. On top of that, we are able to also achieve key distribution. The key distribution means if you want to share the symmetric key, we are able to use this asymmetric key concept. Okay. But the asymmetric algorithms, whatever public key encryption algorithms, they rely on 1 key for encryption purpose and altogether different key for decryption purpose. What is that? KE and KD. And KE is not equal to KD. That's what we discussed a few seconds back. So by doing this approach, there are a couple of important characteristics. Number 1, it is computationally infeasible to determine the decryption key. So that means when I am encrypting with KE, even I do not know what is the KD. Not only me, obviously the attacker should not know what is the KD. Only the KD is known only to the receiver. Okay, so knowing KE, one should not be able to calculate KD. That is one of the most important characteristic of public key crypto systems. Look at this particular diagram. Imagine A is sending a message to B. What A would do? A take that message. That means sender take the message, perform the encryption algorithm. Before performing, I'll talk about the key pair. So A has 2 pairs of keys, that is public key of A and private key of A. Similarly, B also has public key of B, private key of B. Every individual, when they are communicating using public key crypto system, will have a key pair. So we call it as key pair. Now in the key pair, 1 key is known publicly and 1 key is kept secretly. So this is public, this is private. This is private key. Similarly, B also has a public key and has private key. So this private key is known only to B, and the public key of B is known only known to not only B, to everybody. Similarly, in the A's key pair, A knows his public key and as well as his private key. Everyone would know the public key of A, and private key of A is known only to A. Now let us first of all, we should have an algorithm to generate such key pairs at every node. So that means A should be able to generate such key pair, B should be able to generate such key pair. So once you have the key pair, what A is going to do, take the plain text message, take the encryption algorithm. The encryption algorithm is going to take first private key of A. Okay. Okay, private key of A. What is private key of A? PRA, known to A. So first perform the encryption of the plain text using private key of A. Get a particular ciphertext called, say, C or Y. Y is given here, so let us take that as the ciphertext. Now what A is going to do, again encrypt this particular Y or C with the help of public key of B. This is public key of B. Remember, A knows public key of B. So A has taken the plain text, encrypted with the help of private key of A. Then next, encrypted the intermediate ciphertext with public key of B. Now finally we got the ciphertext with this jet. Now this jet is transmitted to the receiver B. The receiver has received this ciphertext. Now what receiver is going to do? Decrypt. First, decrypt the Z with the help of private key of B. The reason is, you see here, this encryption happened with public key of B, and hence the immediate decryption is happening with private key of B. Remember, private key of B is known only to B, no one else, and hence B is be able to decrypt it. So once B decrypts Z, we get this particular Y. Now, how Y we got? We got Y by encrypting X with the help of private key of A. So the decryption process over Y will take the public key of A. Because it is encrypted with the private key of A, the decryption is happening with public key of A. See here. And then the receiver will get the plain text X. Okay. So this is the public key encryption. By doing, if you may get a doubt, see why we are doing encryption 2 times. The reason to perform the encryption 2 times here is that we are trying to achieve a couple of security objectives. What are the objectives? Let us see here. When you look at first encryption, wherein which we are using private key of A, what we are doing is we are doing a kind of authentication or digital signature. This is achieving our authentication or digital signature. The first encryption with the private key of A. The subsequent encryption with the public key of receiver, we are achieving confidentiality. Okay, we are achieving confidentiality. So now if you see in the communication channel, the Z, even if any attacker sees this Z, will not be able to decrypt Z, because to decrypt Z, what is needed is private key of B, and no one else knows that private key of B except B. Okay, and hence we are able to achieve confidentiality. Now once B receives Z and decrypts it with the help of his private key, what he gets is Y, and now Y is getting decrypted with the help of public key of A. So that means B is able to now know that this particular ciphertext is sent by A, and this is what is authentication. So we are achieving confidentiality and we are achieving authentication by performing public key encryption in this particular order. I hope we are good to go. Any doubts or any comments or any clarifications so far? Proceed. Okay, yeah. So we'll proceed. So if you see here, by doing this public key encryption, we are able to achieve number 1, encryption and decryption. Number 2, digital signature, mainly meant for authentication purpose. And also we are able to implement key exchange. What is this key exchange? That we will discuss little later. This particular key exchange is mainly, when we discussed that symmetric key, the challenge is how to share the key. So sharing of that particular symmetric key can happen with the help of asymmetric or public key crypto system. That's what is the key exchange. So what are the various algorithms for public key crypto systems we have? We have RSA, we have elliptic curve, we have Diffie-Hellman, we have digital signature scheme. These are all various public key encryption algorithms that are currently available. Now, as I said, we will focus on one particular public key encryption algorithm, which is RSA, because our quantum algorithm, which is Shor algorithm, is trying to break this particular RSA algorithm. So let us see what is RSA. RSA is a popular encryption public key encryption algorithm. So it is a public key encryption algorithm. So it is implemented. It was proposed in 1977 by three famous security professionals, Rivest, Shamir, and Adelman during 1977. Number one, it is also a block cipher. That means it processes the plain text in terms of blocks. Okay, and it uses a key length of 1024 bit and more. So that means it is providing a larger key space. Okay. Of course, there were smaller key spaces, but they were found to be vulnerable. What is this algorithm? The algorithm goes this way. We generate two large distinct prime numbers p comma q. First step is we generate two large distinct prime numbers p comma q. Remember, p and q should be of same size. Then we are going to calculate their product. So n is p into q, means n has prime factors. This is the most important observation here. So p comma q are prime factors of n. So what we did, first we took the factors, we got the number n. Then we are going to calculate Euler's totient value over that particular n. Euler's totient value is represented as psi of n. In general, psi of n is calculated as p minus 1 into q minus 1. What is Euler's totient value? It is the number of positive integers that are less than n and also relatively prime to n. What do you mean by relatively prime to n? Imagine there is a number x. If it is relatively prime to n, that means GCD of x comma n is 1. Okay. So we calculate Euler's totient value over n by performing p minus 1 into q minus 1. That is the third step of RSA. And the fourth step is we select a random integer e such that the condition is e should be less than psi of n and also e should be relatively prime to psi of n. That means GCD of e comma psi of n is equal to 1. So far we have come across 4 steps. We took two large prime numbers, we calculated their product, then we calculated Euler's totient value of the n, then we have picked a random integer e satisfying the condition that e is less than psi of n and e is relatively prime to psi of n. Then the next step is we calculate a unique integer d such that and e are multiplicative inverse. Okay, how do I write that? Ed is congruent to 1 mod psi of n. So the relation between E and D is E and D are multiplicative inverses at mod psi of n. And remember, D should be again relatively prime to psi of n. So far we have seen 5 steps. If you see the 5th step, what we have done is we have calculated a D such that D is multiplicative inverse of E. How do I write that? ED, when I multiply, it is congruent to 1 at mod psi of n. What I have finally is I have the public key n comma e, the private key is d. So that means so far whatever the steps I have made is for key generation. So far the steps that I have made is for the key generation. I'm considering NE as the public key and D is the private key. So these steps have to be calculated at every node so that every node will have the key pair. What is the key pair? The public key and the private key pair. This is how I generate keys. So we can call this as the key generation steps. Now, once I have the keys, how do I do the encryption? To encrypt a plain text M, what I'm doing is C is equal to M power E mod N. That's all. And the decryption is the reverse process of it. I take the ciphertext, I take C, and the plain text is M is equal to C power D mod N. So previous slide we have seen the key generation, wherein which we said E comma N is public key and D is private key. So I have used public key for encryption purpose, the private key for decryption purpose. So how do I do the decryption? M is equal to C power D mod N. How I am doing the encryption? C is equal to M power E mod N. So this is public key. Okay. So my encryption and decryption are done. I have already discussed the key generation process. Now, if you look at the ingredients of the variables of the algorithm, you can see that P, Q are the prime numbers, which we have chosen. And remember, we kept them private. Nobody knows. We calculated their product N and it is made public. You see, N is there in the public key. Next, from N, we have calculated psi of N, and then we have chosen an E such that GCD of E and psi of N is equal to 1. And remember, E is publicly available. See here, E is the public key. Now, what is D is calculated, which is a multiplicative inverse of E at mod psi of N. And remember, D is kept private. Okay. Now, the point is, if an attacker wants to attack the RSA, or in the sense, derive the plain text from the ciphertext, what the attacker has now is attacker knows C. Attacker has C, obviously, and attacker also has N comma E. Now the question is, can the attacker calculate D? Can the attacker calculate D? So if you see, D is the multiplicative inverse of mod psi of N, and E is available publicly. And remember, N is also known publicly. But is it that N alone is sufficient enough to get my D? I need psi of N. How I am getting psi of N is P minus 1 into Q minus 1. So that means I should know these two prime numbers P comma Q, who are the prime factors of N. So an attacker needs to know prime factors of N. Then only he will be able to calculate D. So from N, can the attacker calculate its prime factors? The question is, we don't have algorithms or computationally feasible algorithms in a conventional classical scenario to calculate the prime factors of N. So factoring the number is the main cornerstone of RSA security. So where is the security of RSA algorithm? The security of RSA algorithm lies with number factorization. So factoring really large numbers into their prime factors is extremely difficult for the classical computers. So that means knowing N, deriving P comma Q, which are the prime factors, is extremely difficult for the conventional computers, the current generation computers. Especially we are talking about the keys of size, say 1024 bit, 2048 bit, etc. more and more, the larger number of keys. So it is impossible for the current generation systems. So just for your feel, you can look at a 2048 bit number. If you are representing a 2048 bit number in a decimal format, this is one number, one particular number. Now, how do you find the prime factors of it? using a conventional computer, there is no computationally feasible algorithm for this particular purpose. And because of that reason, we are able to implement RSA. Because of this particular reason, RSA is proved to be secure. So ironically, security of the RSA lies with the fact that we are unable to solve a problem. Okay, what is the problem? The problem to find the factors, especially the prime factors of a given number. Okay, so that is the strength of RSA algorithm. So when you notice in 2009, Moody has factored a 512-bit RSA key. It took about 73 days. Subsequently, 768-bit RSA key was also broken, but now current standard is 1024-bit and more, which is conventionally computers, it is difficult to break it. That is about RSA. There is one more algorithm called Diffie-Hellman key exchange algorithm. This is the first published public key algorithm, and it depends. The strength of this particular algorithm depends upon the strength that we don't have a computationally feasible algorithm to calculate discrete logarithms. Like we don't have a feasible algorithm to find the factors of a number. In a key exchange algorithm, Diffie-Hellman key exchange algorithm lies with the fact that we don't have a computationally feasible algorithm to calculate the discrete logarithms. I don't spend much time on this Diffie-Hellman key exchange, but the idea of the key exchange algorithm is that both communicating parties, Alice and Bob, by executing this algorithm, they will share a common key. They will get finally a common key. Okay, so once they have common key, obviously they can communicate using a symmetric encryption algorithm, right? So the purpose of Diffie-Hellman key exchange algorithm is to derive a common key such that all the subsequent communications can happen with the symmetric encryption algorithm. The strength of this particular Diffie-Hellman key exchange, similar as I said to RSA, lies with a particular problem that so far we are unable to solve. So classic cryptography, whatever we discussed, lies with the strength that there are certain number theory problems such as prime factorization problem, discrete logarithmic problem. These are all the problems for which we don't have computationally solvable or computationally feasible algorithms. But when it comes to the classical computers, when we don't have the computationally feasible algorithms, in contrast, these problems are able to be tractable or solvable using quantum computers. Okay, so quantum computers or quantum algorithms, they perform a phase estimation in such a way that they solve your factorization problem. Factorization problem is minimized, or the factorization problem is transformed as a phase estimation problem so that we are able to find the factors of the given number. So in 1994, Peter Shor had showed that quantum computers can use these quantum phenomena such as superposition, entanglement, coherence principles, and effectively solve the factorization problem, and we don't rely upon brute force approaches such as the classical computers are using. I'll just quickly give the quantum computing principles that perhaps you have learned in the past few days. So far what we have discussed is, number one, we spoke about the cryptography, we talked about symmetric, we talked about asymmetric, especially we discussed about RSA, we discussed what is the strength of RSA and what is the main problem that RSA is based upon, and now that problem is getting solved by quantum computer. That means when you solve that problem, we will not have any strength to public key cryptography. Okay, so let us see. So far, I think we are good to go. So far, any questions, madam? Any doubts? Madam, am I audible?
Participants, yes. Any doubts? Okay, sir, you can continue the next part.
Yes.
Yeah.
So far we discussed these points. Then we will continue to our next set of concepts, which is quantum computers. So classical devices, we are able to increase the computing performance in terms of increasing the clock speeds, increasing the number of cores, and all that. We are able to increase the speed of speed of the classical computers by following conventional principles. But in 1993, it was shown that quantum computers can be built by violating the Turing proposal. And subsequently in 94, Peter Shor has come out with an algorithm, which is a quantum algorithm. But by then, we don't have a physical quantum computer. So people took that algorithm, but there were no physically feasible quantum computers. Because the reason is nobody knows about how to build a quantum computer fundamental unit, which is the qubit. Subsequently, there were so many developments that have happened in building the qubits, okay, which is the basis for quantum computer. Of course, we have not come to a maturity, but then we are able to play with a few number of quantum bits. And these developments have catalyzed interest among several researchers in developing several quantum algorithms which are exponentially better in performance than classical algorithms. See, whether you wanted to perform solve the problems such as prime factorization, or you want to perform a search over a given set of elements. So these are algorithms from quantum algorithms which are proved to be much more exponentially better in terms of their performance. And the current state of development in quantum computers, we can derive an analogy to the way the conventional computers have grown from vacuum tubes to the current generation chips. The way the classical computers have evolved, the similar phase the quantum computers are also evolving. As we understood in the last few sessions, the quantum computers are built based upon the quantum physics, whereas the conventional computers, they are following the classical Newtonian physics, wherein which the fundamentally they are all deterministic in nature. The output of this result, the computing problems results are deterministic in nature, whereas the quantum principles are based upon the physical phenomena, which is not deterministic, rather it is probabilistic. And hence it has an inherent uncertainty. The beauty of this particular theory is that even though we are having uncertainty, the uncertainty could be mitigated by repeatedly performing that experiment and measuring the outcome such that we come to a common or final conclusion. If you look at this particular theory, any object, of course, you can regard this object as a qubit, which is the fundamental unit of the quantum computer. It does not exist in a completely determinate state or a knowable state. Like in a conventional computer, it would be either 0 or 1. A qubit will have in the state of both 0 and 1. And hence, if you in a physical phenomena, if you observe, this is called wave particle duality in a physical phenomena. And quantum computing is leveraging the properties of quantum physics in terms of superposition, entanglement, interference, and hence performing the computations in a way that is giving much more exponential power than classical computer. all these, the fundamentals of quantum computing, perhaps a few classes back, you must have been discussed. So in the way, if you look at the way the information is represented in a quantum computer, if you want to compare that with the classical, in classical computer, the regular bits have either 0 or 1. Quantum bits, you are having qubits which are similar to our regular bits in implementation, in the sense that we read them either as a value of 0 or 1 in the case of classical, whereas in the case of quantum, both you will have 0 and 1. Because of that, what we are going to do is that we are going to call that as an indeterminate state. We call it as a superposition state. So this diagram represents a classical 0 or 1 state of a bit, whereas for a quantum qubit, you have between you have 0 and 1. You can see that there are probabilistic in nature, in the sense that the measurement is about the superposed states. You can see the probability of being 0 or probability of being 1 in a superposition state. When you look at the way the information is getting processed in a classical computer, basically at the fundamental level, bits are processed sequentially. That's what is the conventional computers, and we are able to solve certain set of problems by implementing sequential algorithms. Whereas in the quantum computing, the superposition qubits are entangled together so that they are giving a parallel phenomenon. So because of that parallel phenomenon, we are able to solve certain problems very quickly. How do you interpret results? In the interpreting results, classical computers, we are having defined states. Results are available in a defined states or deterministic in nature. Whereas in the quantum, the answers are probabilistic, meaning that because of the superposition and entanglement, you have multiple possible answers for a given computation. That's why we are measuring them in terms of their probability. And since it is probabilistic in nature, what we do, the problems are run multiple times, giving a sample of possible answers. And finally, we take increasing confidence in the best answer that is provided. Okay, so we have seen, number one, the way the information is getting represented in terms of the qubits, the way the information is getting processed in terms of a quantum algorithm, the way the information is getting interpreted, the result is getting interpreted in the quantum computer. So representation through qubits, processing through algorithm, and interpreting finally through probabilistic answers. And because of these three differences, they are allowing, these three phenomenon is allowing quantum computers to solve certain classes of complex problems efficiently than classical computers. So just to give a quick difference between the classical as well as quantum, the way the information is stored, the way the information is processed, the way the information is represented. If you see, the classical computers are based on bits, and information is processed using the conventional logic gates such as AND gate, NOT gate, OR gate, and they are all obeying the classical Newtonian physics principles. You represent the information in terms of binary codes, in either 0 or 1, and operations are represented by performing Boolean algebraic operations. What are the advantages of conventional computers? There are no limitations about measuring, especially, and the circuits are easily integrated into a chip. The basic disadvantage is that they are slower in nature, and hence certain problems are not solvable. When it comes to quantum computers, the quantum information is getting stored in the form of quantum bits, and it is stored by using an electronic spin operation. Then information is processed with the help of quantum logic gates. There are several quantum gates are there. Using those gates, information is processed in the gate-based quantum computers. There are adiabatic quantum computers. Like that, we have different ways of processing the information. All these operations are governed by quantum physics, and the information is represented in the form of qubits. Operations, what we are performing when it comes to the classical, when we perform Boolean algebraic operation, the quantum computer performs operations over the Hilbert space. That means the complex number space. The advantages of quantum computers is that they are faster than classical computation, and hence we are able to solve certain complex problems. The basic disadvantage of quantum computer is that they have higher error rates. Answers are probabilistic in nature. Here it is deterministic in nature, whereas your quantum is probabilistic in nature. One side it is advantageous, and at the same time it is also disadvantageous to address certain problems. So we have looked at the classical, we have looked at the quantum computer differences, the way they get processed. And I just skipped this, the way the qubits are getting implemented. These are all the basic benefits of the quantum computing. You are having superposed states. The system is probabilistic in nature. Any given state can be observed. So entanglement is another benefit of quantum computing. And then all these principles are under the wave-particle duality. So these properties are exploited for quantum computers in various fields such as cryptography, sensing, key distribution, etc. Now, we have seen security algorithms, we have seen quantum computing principles. Of course, I have not gone in depth of quantum computing principles because already these principles were discussed in the past few sessions. Now, what is the impact of quantum computing on the cryptography algorithms? If you see advanced encryption standard, which is symmetric algorithm, the impact of the quantum computer is not much. But when it comes to the symmetric algorithms such as asymmetric algorithms such as RSA, these algorithms would no longer be secure. The reason is that we are able to find the factors of a large number using quantum computers. A classical computer cannot solve that particular problem, whereas the quantum computer is able to solve the problem of finding prime factors of a given large number. And hence, obviously, all other public key algorithms would no longer be secure. Is it that the quantums do not have impact on the symmetric? Of course, there is impact, but you can increase the key space of symmetric encryption algorithms and you can make them secure. But when it comes to public key, you can see that all these algorithms would no longer be secure. So why? What is the reason? What is the algorithm that is making this public key algorithms no longer secure? Is the basic algorithm is the Shor algorithm. The Shor's factorization algorithm is one of the basic example which is demonstrating the quantum computer potential. So which is able to solve a problem a conventional computer or a classical computer not able to solve, right? So this particular algorithm is able to solve it. Okay, conventional computers are not able to solve. The Shor algorithm is demonstrating the ability of quantum computer to solving a particular problem. Okay. So what is Shor algorithm? Peter Shor has invented an algorithm in the 1994 for a quantum computer. That algorithm could be used to find the prime factors of the integers. Remember, this is the problem that we are talking about as the strength of RSA, right? You have remember P comma Q. We have calculated n is equal to P into Q. We know n, but we don't know PQ, right? So identifying the prime factors, we don't have a classical algorithm to calculate, whereas the Shor has built this algorithm. The aim is to find the prime factors of the integer n. This factorization, what the Shor has brought is he has related it to finding a period over a particular function. We will see what is this function about and how it is getting calculated. So that particular function f over x at a n variables is a power x mod n, where a is any randomly chosen private integer a less than n and also co-prime. That means GCD of a comma n is 1, and hence which has no common factors with n. Peter Shor has built the algorithm to solve this particular equation. That algorithm, when it is implemented on a quantum computer, is able to identify the factors of the given n. So what I do is I will give you that algorithm step by step. I have not taken the slide, rather I will going to explain it through this writing pad. So the algorithm goes this way. The Peter Shor algorithm, first step 1 is, imagine let n be the number to be factored. Okay, let the number n to be the factor. We wanted to identify the factors of n. So the second step is we choose a random number k. Choose a random number k such that the condition is that 1 is less than k is less than n. This is the second step. So third step, calculate GCD of n comma k. Of course, in order to calculate the GCD of n comma k, you have famous algorithm called Euclid's algorithm. Okay, you have Euclid algorithm. If GCD is n comma k is equal to 1, then we go to step 4. If it is not 1, that means we have factor. If the GCD of n comma k is not 1, then we know we have the GCD value of n comma k is the factor we are looking at. Okay, so typically we go to step 4. So that means GCD is 1. What is step 4? The step 4 is an important step. So for a function f of x is equal to k power x mod n for a particular function defined as k power x mod n, the objective is find a smallest integer. Find a smallest integer called r such that f of a for any a is equal to f of a plus r for any a. We need to solve this particular step. Step 4 is for a function f of x is equal to k power x mod n, we need to find a smallest integer r such that f of a is equal to f of a plus r. Now, how do I do it? So step 4.1 is, imagine, let us take some integer q is equal to 1. Then step 4.2, what I do, calculate q into k mod n. So once I calculate q into k mod n, if it is equal to 1, then what I do, I go to step 4.3. Otherwise, what I do, I'm going to redefine Q as Q is equal to Q into K mod N. So that means I am reassigning Q to the remainder. Okay, so that means I'm reassigning Q to the remainder. Okay. And then what I do next is I repeat 4.2, this step 4.2 till I get Q into K mod N is equal to 1. So once I get Q into K mod N, I go to 4.3. Otherwise, I make Q is equal to Q into K mod N. So that's what I'm doing it. And remember how many times of repetitions I am doing. Okay, track number of repetitions I am making. Okay, please mind the, don't worry about the spellings. So next step 4.3. In step 4.3, what I'm doing is I have tracked the number of repetitions. I am calling that R as number of repetitions or rounds in 4.2. Okay, so what I did in 4.3 is I just took the number of repetitions or round as R. Okay. Next, I have step 5. So all 4.1, 4.2, 4.3 is part of 4. Now I'm going to step 5. What is step 5? If R is odd number, then go to step 2 and choose different K. I have to repeat the process. Okay. If R, that means the number of repetitions that I have made in my 4.2 is odd, I'm going to step 2 again. Okay, and choose a random number, another random number K, again start the process. Okay, if R is even, I go to the next. Okay, so that is my step 6. Okay, what I do is choose the remainder value. Choose the remainder value in my R by tooth round in step 4.2 and call this as P. Okay, so that means imagine I have in the previous slide, whatever the R value is even. What I'm doing, I'm checking what is the remainder value that I have in this 4.2 for my R by 2 to round. That means imagine R is equal to 6. My R by 2 is 3. In my third round, what is the remainder value? So that is if R is equal to say 8, my R by 2 is 4. So I check fourth round remainder value. That's what I do. That's what I do. And that I'm calling it as P. Now, if the condition, if P plus 1 is equal to N, that means the number that what I wanted to factor, then I go to step 2 again, choose different K. I choose a different K. If not, I go to step 7. What is step 7? Step 7 is my factors of N are My first factor is GCD of P plus 1 comma n, and my second factor is GCD of P minus 1 comma n. Okay. So that's all I have. So totally 7 steps. So let us have a quick look at that. I have a number to be factored. For that, in the second step, I have chosen a random number k which is less than n. Then I checked whether the GCD of n comma k is 1. Then I proceed further. If not, the number what I have chosen is the factor. But it is a very rare occasion that we will choose such things. So step 4 is about we are trying to solve a particular equation. This is the crux of Shor algorithm. What is that step 4 says? Find for a function f of x is equal to k power x mod n, we find a smallest integer r. What is the condition of that r? F of a is equal to f of a plus r for given any a. So I took a number q, where q is equal to 1 initially assigned. Then I calculated q into k mod n. If it is 1, then I go to the subsequent step. If not, I repeatedly reassign the values of q as q plus 1, q into k mod n. I'm reassigning the remainder to the q. I repeat it till I get the remainder as 1. And remember, I am tracking the number of such repetitions or rounds I am making. And that number I am assigning it to the value r. If my r is odd, I go to step 2. If not, I will go to the next round. Next step. What is the next step? I choose the remainder value in my r by 2th round in my step 4.2. Remember, as I said, the value r should be an even number. So obviously I am checking r by 2th remainder value, and that I am calling it as p. Now one more condition I am checking. If my p plus 1 is equal to n, I go to step 2 and choose a different k. If not, I go to step 7. What is my step 7? Is giving me my factors f1 and f2 of the number n. So this algorithm, if you look at the whole step 4, whatever the step 4 we discussed is related to finding the value r, which is called the period. Okay, which is called period of the function f of k comma n of x is equal to k power x mod n, and your k values are ranging from 0, 1, 2, so on up to n. Okay, so that means your step 4 is about finding a value called r, which is called as a period. Okay, for a different values of k ranging from 0 to n. So this is the Shor algorithm. Now, what is that interesting aspect of this particular step 4? So if you see here, imagine you have, say, n is equal to 21. Okay, I am taking k value as 11. Okay, so what is my GCD of these two numbers is 1. Now what I do is I'm just trying to find for different values of say x values, x is equal to 0, 1, 2 and so on. I am finding, okay, f of kn of x is equal to k power x mod n. Now if you see here, okay, let us start with f 11, 21 of 0. If you apply, so that means your k value is 11 power 0 mod 21 is 0, right? F of 11, 21 of 1 will give you the value 11. Similarly, f of 11, 21 of 2 will give you the value 16. F of 11, 21 over the value 3 gives value 8. F of 11, 21 over the value 4 will give you the value 4. F of 11, 21 over 5 will give you the value 2. Then f of 11, 21 over the value 6 gives you the value 1. F of 11, 21 over value 7 gives you 11. So that means, okay, sorry, this is 1. 11 power 0 mod 21 is 1. Then 11 power 1 mod 21 is 11. So f of 2 is 16, f of 3 is 8, f of 4 is 4, f of 5 is 2, f of 6 is 1. So f of 7 is 11. That means you notice that you are repeating the sequence, right? Now imagine if I am calculating f of 11, 21 over 8, obviously I'm going to get 16. Similarly, f of 11, 21 over 9 is going to be my 8, and so on. So that means you see here, I have a sequence of numbers 1, 11, 16, 8, 4, 2, and again 1. So this is the sequence I am getting, and that particular sequence period is, in this case, is 6. So this is called period. Okay. Now this is the interesting step of Shor algorithm, finding the period. Right. Once this period is found, you are able to calculate. The factors. Right. Because what we did, once you have the period, you have checked what is the remainder value in that particular r by 2th period, r by 2th round, and that particular value you called as a p plus 1 you checked whether it is n, you go to the step 2, otherwise you choose a different k. Okay, so finally we are able to calculate factors f1 and f2. Of course, using p, but p has come because of r. So this particular step is calculating your, the r is period calculation in Shor algorithm. Now, what we discussed is the calculation of period. How it is done in the quantum computer is, it is done with the help of considering all possible values of k by encoding them in terms of, the qubit values, right? So superposition of all pairs of your k power x mod n are represented in the form of a superposition, and then subsequently a quantum Fourier transform is applied over these superposition values to derive the value r. So this is how the Shor algorithm is calculating the period r, and from the period it is calculating the factors. I'll just show the structure. You can see here the random number generator. Then if you see here in the whole process, your step 4 is the one which is happening in the quantum computer. Rest are all are happening in the classical computer. Okay, these are all happening over the classical computer. Only the step 4 is happening in the quantum computer. That means the calculation of r is happening in the quantum computer. So this is the gate representation of your quantum process of Shor algorithm. You typically take two registers X and Y. One is used to represent all possible combinations of your f of function f of x, that is x power k mod n, and one register is used to store all the values. One store the values of the calculation, then perform the function, and the result you are going to use the quantum Fourier transform, then finally calculate the R value. This is the gate representation of the Shor algorithm. And because of this algorithm, we are able to solve the factorization problem on which RSA is based upon. Now, having said that, is it that the current algorithms or current the quantum computers are able to solve the RSA implementations over the um, various protocols, various the applications, various security mechanisms that currently be in place? Absolutely not, because after all, the current quantum computers are playing with a few numbers of qubits, say maybe around 50 to 100 range. Only the qubits are there, but there are some news coming in that there are some implementation over about 1,000 qubit. But what are the number of qubits that needed to break the RSA in a practical scenario is much more larger in number. Implementing such number of qubits with the current day technology needs a lot of effort, in the sense that there are so many other problems such as decoherence and all that, making the practical breaking of RSA currently not available. But having said that, there are days to come. The public key cryptography has to be totally relooked at it in building a new public key cryptography algorithms. This is about Shor algorithm. As I said, if you see the whole process of Shor algorithm, though there are algorithms that are such as number field sieve, which are going to calculate the factorization problem, the Shor algorithm has very less amount of complexity in terms of or speed up when compared with the other algorithms that are there. So what I suggest is, if you really want to play with the Shor algorithm, please take some, the examples that are there in the online, and then play with the algorithm that what I have seen, maybe with a couple of 2-digit numbers, and then try to implement the factorization algorithm in any one of the platforms such as Qiskit, so that you will be able to see the quantum effect. So this is about Shor algorithm. Any doubts you have for the Shor algorithm? I'll be happy to mention.
So I have a few doubts.
Yeah, please.
So what is the exact qubit needed for the Shor algorithm? You have mentioned it is a lot. So what is the exact qubit?
No, the one what actually people have tried is with a single digit qubits. But in a practical scenario, you need several, thousands of qubits that are needed to break the numbers that what I have shown. So take an example. If you look at the RSA, the 1024-bit number that I have shown, I think a few slides back, in the current scenario, it is not possible. Maybe people are expecting that we will be able to implement such a qubit system maybe in a decade time. So that means you have another decade time in a loose sense.
Okay, sir. So what about the communication protocol? Like in internet, we have TCP, IP, these protocol for communication. So do we have the protocols in place for quantum communication?
So you mentioned about the TCP/IP. So basically, the internet, uses the TCP/IP communication protocol stack. Again, security is implemented at, your application layer, then your transport layer and network layer using various protocols such as IPsec or TLS. And again, in those protocols, you have wherever the public key is there, all these public key encryption algorithms are at risk. That's the slide which in fact I have shown you here. Your implementation, security implementation is having RSA or digital signature scheme or the Diffie-Hellman key exchange or elliptic curve scheme. All these schemes would no longer be secure. Okay, the only thing is that we do not right now have a quantum computer that can actually break the current industry standard. What is the current industry standard of a key? Say 1024 bit and above. So we don't have that computer with such a number of qubits to break it. Okay, so that is the only relief that we have. But down the line, it is expected that number one, there is a growth in terms of software libraries such as Qiskit, Q-sharp and all that. And subsequently, there is also the realization of qubits, especially in removing addressing the noise of the qubits. There is a progress. So all this is expected that down the line of say 10 years, it is expected that these algorithms are to be replaced. But for that, whether it is your at network level security or at your transport layer security or per se application level securities. So wherever your public keys are there, they have to be replaced. The current schemes have to be replaced. Okay.
So I had another doubt.
Yes, please go ahead, Amma.
So even if we have states that are in superposition, but still we are computing every state, right? So how is it faster? Is the switching time of this states faster? So how is it faster? That's what I'm asking.
How is it? Can you please repeat? How is that?
See, so every states are in superposition, right?
Correct.
For given set of qubits, say 30 qubits. So for 30 qubits, every states are in superposition. But still, during the calculation, we are computing and testing every state, right? Every combination of state.
Correct. Again, yeah. When you are asking the question, I think you are visualizing in your mind that these calculations are happening sequentially. But rather, you should think that when all these states are in a superposition state, the computations are happening parallelly. Remember, actually, if you look at here, what I have mentioned, this particular, the period calculation step. You look at this particular scenario, of course, I gave the case of a two-digit number, n is equal to 21, k is equal to 11. Even if suppose in a, my x values would go 0, 1, 2 up to say 21. But the point is that you look at a number which is, I said about 1028 bit number, which is a massive number. And now you have to explore what could be the possible values of this particular function. All those values are represented using the qubits, number one, and calculations are happening in parallel over those qubits. That is where your massive computational power that is coming from quantum computer, right? So you should imagine, okay, for your imagination purpose, I'm just telling, you can think about them as multiple threads running at a time parallelly. Okay, so with such an enormous computations, only we are able to solve. That's where the power of quantum computer is coming, because with all those superposition states, you are performing calculations, and don't think them in terms of sequential in nature. It is parallel in nature.
Okay, sir, understood. Thank you.
Right. So now the point is, this is the period calculation, and this is its corresponding gate representation. Okay, so you can check the corresponding implementations in various toolkits. And one more important thing that you need to observe is that the whole Shor algorithm, only that step 4 is implementing on the quantum computer. Remember, the earlier steps, step 1 to 3, similarly, step 5 to 7, they are all implemented on a classical computer. Okay, so that means, you can see the handshake between your classical. You can see the handshake between a classical and quantum to classical. Okay, so that's the beauty of this algorithm. It's not that the whole algorithm is getting implemented on quantum or not on classical, right? It's getting on classical 1 2 3, moves to the 4, then calculate, come out, check. If it is required, you are repeating with the k. Remember that. Okay, so this is the whole ball game of the Shor algorithm, right? In calculating the factors of the number. Now, so we have checked Shor algorithm, which is solving the fundamental problem on which RSA is based upon, which is factorization problem. Okay, this is about asymmetric encryption. But before asymmetric encryption, we felt that the problem of key distribution, where this key distribution comes into picture in symmetric algorithms, right? In symmetric algorithms, what is the challenge? How do I share the key between the two communicating parties, the common key? Okay, so the common key should be shared between Alice and Bob such that the communication can happen in symmetric manner, or a symmetric encryption algorithm. What are the various techniques that what we have? We have multiple techniques. Number one, this particular symmetric key can be distributed using symmetric encryption algorithm. That means, imagine Alice and Bob wanted to communicate using symmetric encryption algorithms such as AES. They need a key. This key has to be shared. How this key can be shared? Again, using symmetric encryption algorithm. That means there must be a master key, M. This would be used to encrypt your K. So Alice uses the master key to encrypt K and then give it to Bob. Bob will use that same master key to decrypt and get that K. So this master key is M. This particular K that is shared is called session key. Okay. Of course, we have another challenge is that how do I establish master key? That is one of the fundamental challenge. There are key distribution centers we have. There are various approaches for that particular purpose. But there is one more scheme. The scheme is exploiting asymmetric encryption. The symmetric key, that K, can be distributed between Alice and Bob using asymmetric key. That means Alice and Bob have their public key, private key pairs. Okay, Alice and Bob have public key and private key pairs. What Alice is going to do? Create a session key, encrypt it with the help of public key of Bob. Okay, encrypt it with the help of public key of Bob, send it to Bob. Bob will decrypt that with the help of private key of Bob. So decrypt it with the help of private key of Bob, and then so imagine that, see, this encryption is C. So decrypt it with the help of private key of Bob. Bob bits key. So now communication happens with symmetric. So that means I have used public key philosophy to exchange my key. Remember, in practical scenarios, in most of the practical applications, the symmetric key distribution using asymmetric encryption is the one that is getting implemented. The reason is generally asymmetric keys encryption is not used for plain text communication. asymmetric encryption is used for the purpose of symmetric key sharing. Why it is so? The reason is that, first of all, asymmetric key encryption itself is computationally challenging. What is the computationally challenging aspect of asymmetric? If you look at the RSA algorithm, though it looks that you have about 5 or 6 steps for key generation, 2 steps for encryption and 2 steps for decryption, but then you look at the numbers that are to be generated randomly. Calculations takes enormous amount of time, and hence symmetric encryption algorithms are computationally less sensitive or intensive than asymmetric encryption algorithms. So that's the reason why plain text communications typically happens with symmetric encryption algorithms. But obvious challenge is symmetric encryption algorithms key has to be exchanged. So key would be exchanged with the help of public key techniques. You may think that, sir, anyway I'm implementing public key, but the point is that plain text would be of variable in length. That means plain text could be of any size, whereas key is of limited in length. So that's the reason why key would be distributed with the help of asymmetric encryption, and the plain text encryption happens with symmetric key distribution. So that is what is the practical scenarios or practical applications use case. But now, when once your asymmetric encryption is in danger with the help because of the quantum algorithms such as Shor, how actually your key sharing can happen? Because your asymmetric encryption is getting no longer secure. So how do I share the keys? For symmetric encryption, again you have principles of quantum computing comes into picture, especially your quantum superposition, entanglement, and the uncertainty principles. These are all the 3 properties that are getting used in key distribution problem, and hence you call that as the quantum key distribution. So in quantum key, for quantum key distribution, there is a popular algorithm which was proposed by Bennett and Prasad in 1984, and it is called BB84 algorithm, which is the first cryptographic protocol that is used for key distribution. It is used for key distribution. So remember, once your key distribution problem is solved, you can very well use symmetric key encryption algorithm. And remember, symmetric key encryption algorithms are not having much problem from quantum computers. Only thing is that you can increase the key space. Okay. So unlike your asymmetric algorithms, which are no longer secure, symmetric algorithms are not vulnerable towards quantum computers. So your encryption can happen with symmetric encryption. Only thing is, how do you share the key? Because asymmetric is in danger. So use quantum principles to distribute the key. So the popular algorithm, as I said, is the BB84 algorithm or a BB84 protocol. So you have a sender, you have a receiver. Now both of them, they have to communicate in a symmetric. For that purpose, they need a key. So Alice is the sender and Bob is the receiver. So Alice wants to send the key. Now when Alice wants to send the key, the current standard is use asymmetric encryption such as RSA or Diffie-Hellman or whatever it is, share the key. But we said asymmetric is in danger, so we are going with this particular protocol, BB84 protocol. So imagine the Alice wants to send this particular key or establish a key that have the bits 0, 1, 1, 0, 1, 0, 0, 1. So what Alice is going to do is, Alice is going to consider sharing of these bits not through kind of our traditional mode of thing, but rather in terms of ray of light using the photons. But while implementing that ray of light, in the series of photons or a ray of light, what actually Alice is going to apply is, Alice is going to put a filter. That filter is called the basis. The filter looks as a rectangular or a vertical or a rectangular filter, which is represented as plus, or a diagonal filter which is represented as X. So these are all filters, or you call them as bases. Now your typical 0 in this particular filters will have any of the key bit that you wanted to share will have 4 possible states, in the sense that when you say 0 and 0 in a with a filter, the rectilinear filter, or you call it as a horizontal vertical filter, 0 is represented with a up arrow, 1 is represented is in a horizontal arrow like this. On a diagonal filter, 0 is represented in this manner, and similarly 1 is represented in this manner. So that means this is, you can think it as a 0 degree, 90 degree, this is about minus 45 degree, and this is about plus 45 degree of angle of light. Okay. So now Alice wants to send these bits, apply the filter or else the basis. Remember, this application of filter or basis is happening randomly. Okay, it is happening randomly. So when once this filter is applied, you see the output of that particular filter as per the the possible states that we have. So when a 0 is sent over the corresponding rectilinear base, you get this corresponding state. Similarly, when once 1 is sent via rectilinear base, you get the corresponding state like this with 0 degrees. When 1 is sent over the diagonal filter, you get the state of minus 45 degrees. Like this, you get all these states, and then the light is sent like this over the quantum communication channel to Bob. Now, what Bob would do? Bob would receive these, the photon states, and then apply his filter. When Bob is applying this filter, Bob will apply again randomly. Okay, he do not know what is the filter order or the basis order Alice has applied. So imagine he is applying in this particular order. Then what he get? So you see the state is this, which is at 90 degree up. When he applies the basis, which is rectilinear basis, he get 0. In this particular scenario, both are same. Now look at the second bit state. Actually, Alice has sent 1, and the corresponding photon state is which is 0 degree state. And when Bob has applied the the diagonal filter, he gets the value 0. Okay, so which is not correct actually. Similarly, for every bit you can check all the corresponding states that Alice has sent, and when Bob has applied the filter, what are the bits that Bob has received. Now the point is, Bob will tell that yes, this is the Bob will tell that this is the filter I have applied. Is it correct? This announcement happened in the classic channel. In the classic channel, that means in a regular communication channel, Bob will tell Alice that, look, this is the filter that I have applied. For that, Alice will say, yes, you have applied the right filter, or say, no, you have not applied the right filter. Okay, so that's what is the channel announcement. So in the quantum channel, you are sending the states, and in the classical channel, you are announcing the basis for these states. Okay. So in the quantum channel, what you are doing is you are sending these the states, and in the classical channel, you are announcing the basis, and then say that yes, basis is right, or no, basis is wrong. Okay. So if you see here, as per that, let us take another example, A and B. A wanted to send these bit positions, and he or she has applied the corresponding filters, bases or filters, and the corresponding light polarization angles I have told. And then the receiver B, he has applied randomly at different filters. You can notice a different filter here. You can notice a different filter here. When these different filters are applied, when these measurements are different, you can see that those differences would be omitted. Wherever these correct filters are applied, wherever they say that yes, you have applied the correct filter, only those particular corresponding bits are considered and they are taken as the key. Okay, so finally the common key is taken as the states where correct filters are applied. Okay, so finally the common key is 1101. Now A and B has the established common key. Now imagine if any eavesdropper or an attacker listening to this communication channel, if he listens and if he wants to measure, what will happen is it is going to induce the errors into the, it is going to induce errors into the system, or else either they will collapse this particular quantum states. The reason is, all of you must have learned that any measurement of qubit, what it will do, any measurement of qubit will collapse the system. So point is that number one, both A and B are able to share the key. A and B cannot prevent Eve listening to this communication channel, but they will come to know that yes, Eve has listened the communication, so they can restart key sharing process. So BB84 protocol is meant for sharing of the keys in this particular manner. And remember, as I said, Eve can listen to the channel. You may try to capture the key, but any such type of listening to the communication channel and capturing the key will be informed both to the sender and receiver, and hence they will be able to restart the key distribution or key establishment process. So once the key distribution happens, once the key establishment happens, both A and B can communicate using symmetric encryption techniques such as AES. This is about BB84 protocol. So what is that we have ahead? If you look at, we are going to build, number one, quantum resistant algorithms in terms of we have lattice based cryptography, which is one of the becoming popular algorithm, and these are all comes under post quantum cryptography. Okay, it is comes under post quantum cryptography. But the point is that in a longer term, when we have quantum hardware that is getting into maturity, we need to look for altogether different protocols, and there are already steps that are happening. NIST has constituted several the challenges given to the people to come out with post quantum cryptography. That means to resist the able to withstand the quantum attacks. Okay, so with that I will just conclude the talk. I hope that all of you are able to follow. So we have discussed the security principles, public key cryptography algorithms, the strength of public key cryptography algorithms, the current classical computers are not able to solve certain problems such as factorization problem or a discrete logarithm problem. Then we have seen quantum computing principles on a very broader scale. Then we looked at a Shor algorithm, how Shor algorithm is able to identify the factors of a given number. We have seen the algorithm. I suggest all of you to go back on the internet. There are certain the websites as well as the books wherein which whatever the algorithm that I have discussed for Shor algorithm, the working out is already given. So you can play with that algorithm with the small numbers. Then we discussed about BB84 protocol, which is meant for establishment of the cryptographic keys. So with that, I would like to conclude my talk. And if any other questions are there, I would be happy to address.
Participants, if you have any query, please ask, or you can just type. Sir, one question is there in the chat box. Shall I read it?
Please, madam. I'm not able to see the chat.
Shor algorithm is. Please. I will read it. Shor algorithm is susceptible to noise. Each Shor algorithm is susceptible to noise, and if the same circuit is used to process any length of input.
Okay, so number one, the Shor algorithm, what I have discussed, in the slide. Let me go to the algorithm. Okay, the algorithm what I have narrated here is a typical algorithm that one can understand easily, the Shor algorithm. If you see here, there are certain steps that can go in a classical manner. This particular step 4 has to go on a quantum computer. Okay, now number one, is it resisting the resistance towards the quantum errors? Certainly not. Because the current systems we have, they are prone to the quantum errors. And first of all, what qubits we have is the noisy qubits, right? So only thing is that we are able to manage the noise to some extent. So that's why the current generation quantum computers are called NISQ. So noisy intermediate state quantum computers. So it is not that they are not prone to the noise, number one. Number two is the current qubits are prone to the noise, and hence you will expect noise when you are implementing this algorithm. That is one answer. The second answer about that circuit is, this is a very generic circuit what I have given. If you look at the number of bits that are to be there for the qubit, number of qubits that are to be used for register X and register Y are dependent on your N and K. Okay, whatever is your N, whatever is your K, based on that you need these X and Y registers having these qubits. So roughly it is expected that the 1024 bit number is expected around 600 qubits. That's what somewhere I read, that it is expected that we need around 600 qubits to be there. Somewhere I read. So what is the circuit that is shown is a generic structure. Okay. So the number of qubits that are to be there in each of these register is based upon the values that you have, N comma K.
Any other questions, participants?
Hello, good afternoon, sir. I have one question.
Please,
Hello,
madam.
am I audible? Yes, sir. How these quantum computers will affect a bilinear pairing-based cryptographic system?
Can you please repeat, madam? What was that cryptography?
Bilinear pairing-based cryptography.
Okay, I am not sure. I need to check. Can you please repeat? What is that about?
Bilinear pairing-based cryptography.
Okay. Okay. No, I'm sorry. I could not check that. Yeah.
Okay, sir. Thank you.
Any other question, participants? Okay, sir, I have one question. Like, what are the other advantages of this BB84 protocol in quantum computing?
Yeah, so quantum computer is BB84 is mainly meant for the key distribution. So in order to establish the common key between the two communicating parties, so that they can exchange the messages in a secret manner. That means with the symmetric algorithm. That is the main purpose of it. Of course, there are certain attacks on BB84 which are reported which are recorded in the literature. And there are various other versions of other protocols of key distribution. It's not that we have only BB84. Typically, it is widely reported in the literature, in books and various resources, but there are other protocols as well.
Okay, sir, thank you. So as a part of the conclusion of this session, now I would like to extend the vote of thanks on the behalf of Computer Engineering Department and Somaiya College of Engineering and Information Technology. Thank you, sir, for coming and sharing your knowledge and information about the security threats by quantum computing. And it is really a nice session. Thank you once again. All participants, kindly switch on your cameras for a group photograph. Participants, kindly switch on your camera. Okay, thank you very much. Now I will share that feedback link in the chat box session. So kindly fill it.
Shall I conclude, madam, or you have concluded, right?
Yes, sir. Thank you very much once again.
Thank you, madam. Thank you.
Yes, sir. Yeah. And sir, I one request from my side. Please kindly share the PPTs with us.
Yeah. Certainly. I will share this. Yeah, definitely. Via email, I will share it.
Okay, sir. Thank you very much. Just a minute, participants. I will post the feedback link in the chat box.